Okay, let's continue on now. Um, there are two more things I wanted to mention that I didn't finish in the prior video. Um, Let me first change my prompt. I don't like this prompt. I think I've been talking about the directory, whoops, the directory name, and it's nice to, now we can see this is showing my home directory, this is showing that we're in FT analysis, so that'll make it a little more clear where we are. So I set my prompt to this stuff. So anyway, a couple of more details of what I wanted to mention before. So we added that, remember we had some AFNI proc.py, proc, how do you spell proc, come on, py command. We had a bunch of options, and then we were talking about like compare ops to some example. Compare to like example 6b. So what examples can you compare with? So let me do afniproc.py-show, and I'll hit tab, and because I have option tab complete set up with AP search, we can like do show example names, for say. So this shows all the named examples in the help. And just to see what this refers to, I'll do like afniproc.py -h web for the help on the web page. And here are all the examples. Like we've been talking about example, like well, there's a PAMIC example. I'll go back, and here's example 6b that I said was that's a modern task example. So that shows you all the examples you can compare against currently using dash compare ops, or you can compare it to a full AFNI proc command too. But otherwise, these are the set examples that you can compare with. And so, for example, if you want to say, oh, so what is example 6b? If we wanted to see that, well, you could go back to the web page, or you can actually do show example and just say example 6b. Just a little thing, note that this is case insensitive. Lowercase e there is fine, even though it's supposed to be uppercase up there. And I'll do it like that. If I just say show example, where'd it go? So here's my command, and that's just the AFNI proc example. If you add like dash verb 2 to this, it shows the same thing, but it gives like this preface to the example. So talks more about what it's doing. And for example, if we go back to example 6, that's got a lot of the details as to what the options are trying to do. I'll pipe that through less. So no, this isn't quite example recommended as a full example, but it does a lot of stuff, and it describes like the registration steps, why the blur level is what it is, and I don't know. There's a lot of extra babbling there. So that's the more complete example, the more complete help that you would see in the help page on the website, or just running, afniproc.py-help. But if you do this and pipe it through less, that's how many lines? That's 6,600 lines long, 6,000 lines. So it's hard to find things, but if you search for example 6 in here, which that's case sensitive, there's example 6. So this is what you'll see on the web page, and then example 6b. I'll quit out of that. Anyway, I'm just showing a few extra examples, commands that you can use to navigate some things. I'll probably do a video on some of the things that use this, the compare ops options, and more details about the examples, but I just wanted to, mainly I wanted to list the example names so you know what you can compare against. But again, these are just the examples in the help. The other thing that I wanted to mention is, so we modified S05 AP Uber to be a pythonic form just so we can add pythonic as the HTML review style. But is that okay for you, for example, to run on your computer, your laptop, or whatever? The question is, do you have matplotlib installed? So which one should you run now? The way to maybe check that is to run AFNI system check -check underscore all. This is what, we essentially require you to send us the output from this, or we ask you to send the output for this for a boot camp, just so we can make sure people's laptops are prepared for the class. But if I run this, it shows lots of garbage. But the thing that's relevant to the Pythonic form is matplotlib. And if you look under Python libs, so we have some AFNI programs, we have R stuff. It's whining about a bunch of things here, for me at least. And then under Python libs, it mentions matplotlib, and it says module loaded, so it's happy. If this were to fail for you, then maybe you should not run the Pythonic form. So in this directory, that just tells you whether you should run Uber, or if you're possibly able to run the Pythonic form. Accidentally running Pythonic when it doesn't work for you isn't a big deal. It just means you won't get the HTML stuff properly generated. So with that said, now let's focus more on the AFNI proc commands. So let's actually discuss the details. It doesn't matter which one I use. I guess I'll use this one since we just made it. But let's look at the command options, the AFNI proc command options, and we'll briefly compare it to just the pre-generated proc script. That's S15 is the proc script that S05 should generate. And we can just kind of, anytime we want to see what an option might be doing, we can peek at that. For that, I'll probably open a new terminal window. But so let's just cat S05 Uber Pythonic, whatever you want to do. I'll just cat this one since I'm here. So there's the command. It basically takes up the entire window that I have here. So AFNI proc and all these down to execute. So let me just walk through this a little bit to make sure you have a feel for what it's doing. Some of these options are specifying input data. Some of them are specifying quality control operations. Some of them are specifying how we want the data processed. Let's just get a feel for that. Here we say our subject ID. In this case, our subject ID is FT. Again, FT is one of our horses. We have large scanners. That subject ID is like used in the proc script name and in the directory and in many of the file names that are generated. Then we have this blocks option. These are the main processing blocks that the script will go through. It will do more than this, but these are the main ones that we're specifying at least. For example, we're going to do slice timing correction. We're going to figure out how to align the NAT and the API. We're going to figure out how to go to standard space. We're going to align the API to the API base volume, and we'll actually combine alignment with the anatomy and standard space here as well. We'll blur the data. We'll compute some masks that we will mostly ignore. We'll scale the API data. And then finally, after all the pre-processing is done, we'll actually run the linear regression. This is the main point, the linear regression, because the whole purpose of this analysis is to generate the beta weights, to generate the bold response magnitudes, the effect sizes in some template space, so that we can use that for a group analysis. But so with these blocks in mind, I'll just go to the other terminal window. I'll keep this AFNI proc command sitting here. I'll go to my other terminal window, and I'll cd to that same directory and look at the proc script. So cd to AFNI data 6/ft analysis, and now my prompt shows me where I am. and I'll just run less on this dude, or you can use AFNI open if you want to. You can use AFNI open -e on that thing, whichever. I'll use less because then the font size will match my terminal. So I'm not going to go through the details too much here, but so what are these T-shift align TLRC valreg things? You notice there are these big sections, comments with these equal signs. This is an automatic block. If I scroll down, I see a tcat block. Later on, I see an outcount block. Later on, I see, T-shift, align, TLRC. So these are some of the blocks that we specified here. So these are the main processing blocks so far that we're specifying, and that's where you see them. So AFNI proc adds some extra processing blocks on as well, but it does include the things that we specify. So T-shift, align, TLRC. I'll hold the enter key down to just scroll slowly. There's our valreg block. That's the next thing we had here, valreg. And then that's a long block. Blur, mask, and then finally scale and regress. So those are the processing blocks that we're specifying. This actually specifies the order as well. Not all orders are valid, but AFNI proc.py does try to use the order you specify. So that's an important option, the blocks option. Dash radio correlate blocks. This is a quality control option. It's just going to compute at the end of these blocks, at the end of the tcat. If I go back up to the very top here, after the setup block, there's a tcat block used to copy the API data. So this is like the raw data, except for removal of a couple of pre-steady state TRs. So at the end of that block and at the end of the valreg block, after we're all registered, it does these radio correlation computations. So at each voxel and for each run, it correlates the current voxel's time series against a local Gaussian weighted average, a large Gaussian weighted average, like full with half max of. Actually, do we have radio correlate in here? I don't know if this is. Yeah, it is in here. That's good. So here are the radio correlate commands, and this is like computing a correlation against a full with that half max of maybe 20 millimeters, I believe. So it's kind of looking for what happens approximately within the scope of one receiver coil, plus or minus, say. So these correlations, you hope they follow the anatomical structures. If they don't, then you might panic a bit. Anyway, that's a QC, quality control option. Copy and at. Here we specify our anatomical data set. D-sets, maybe it's not the most clear option name. Those are the EPI inputs. So EPI run 1, 2, and 3. So notice these are actually coming from our top dir above is set to FT. Our subject is FT. So subject FT, top dir is also that. So FT / FT EPI run 1 plus orig.head. So back in the other window, I'll queue to quit out of this. If I do ls on the FT directory, so we're specifying the head files. You don't have to include head there. If you use wildcards, you need it to match a full name, but we're not using wildcards, so we could have just stopped at plus orig. But there we have our 3 EPI runs as input. tcat remove first TRs is 2, so we're telling it to remove the first 2 time points from the beginning of every run. Next option. Most of these options, you notice they kind of start with a processing block name. tcat is actually that first processing block. -align. Align is the align processing block. -valreg is a valreg, blur, mask, regress. Those are all processing blocks. So hopefully all options that start with a processing block name refer to that processing block. So these are kind of chronological a bit in terms of how the processing is done, just to help keep things straight. So in the volreg block, we want to align all the EPI volumes to the minimum outlier one, for example. We'll talk more about that when we look at the data, but the minimum outlier volume should be a low motion volume, which should be a good choice for registration, a robust choice. You don't want to pick a volume where the subject happened to move a lot. Backing up to the option we were actually talking about initially, so dash align ops AEA, here we're saying in the align block we want to add some extra options to the main command. And in that case, the command is actually running as align EPI anat.py. So what follows are options that go to that command. So if I look at the proc script again over here, and I go down to, I'll search, well, whatever. I'll just go down slowly so you see. I'll count T-shift align. So here's the align block. And the command it's running in there is align EPI anat to figure out how to align the anat and the EPI datasets. So the options, so that's what the AEA stands for. Any block underscore ops option is going to pass options directly to the program that it references. So in this case, it's align EPI anat. So what follows is a list of options that AFNI proc does not understand. These are not AFNI proc options here. These are align EPI anat options. But AFNI proc will pass them directly to the align EPI anat command. So here's cost, giant move, check, flip, and you see them reflected verbatim in the command. So AFNI proc is not thinking about these options. It's just passing them directly to align EPI anat.py. And as you may have seen in the alignment talk, LPC is a good cost function. The plus ZZ makes it more robust because it initially starts out by using I believe like 6 cost functions, and to make sure that the initial alignment isn't wacky for some reason, but then it finishes off with LPC. LPC is the local Pearson's correlation that's looking for correlations with opposing contrast, because white gray CSF in a T1 image, for example, in the anatomy is going from bright to dark. White is bright, CSF is dark. But in the EPI dataset, our volume registration based dataset, the contrast is opposite. CSF is bright in the EPI, then comes gray matter, then white is actually darkest. So with the opposing contrast, we use local Pearson correlation, which is actually looking for the opposing contrast there. And then giant move, we allow them to be a little farther apart initially, and we're going to check to make sure or check to verify or get some support as to whether the left is consistent between the anatomy and the EPI, or is, as we have seen in many public data sets, public repositories, left and right can be actually backwards between them, which isn't going to, that's not going to be something you want to realize after you've published a paper. Oh, I had left and right flipped. So this is a QC. It gives us a QC measure and image to evaluate whether left is consistent between those two data sets. So that's this option. We talked about aligning to the min outlier. We'll see that in the script too. That's not important. But it specifies, this is more relevant to if you're not going to standard space. In a ridge space, we're saying align the EPI to the anatomy rather than the anatomy to the EPI. In this case, it's kind of irrelevant because we're going to standard space anyway, so it doesn't matter too much. But, so the next option, indeed it says to, so here's a TLRC block, but that's computing how the anatomy aligns to a template. The volreg TLRC warp option is telling AFNI proc that we want to send the EPI to standard space using the same warp that was computed for the anatomy. So basically, we know we're going to align the EPI to an EPI base volume. Then we're going to warp the EPI to the anatomy to align to the anatomy, and then to standard space. And we'll combine all of these operations into one within the volreg block. Blur size 4 millimeters. So in our blurring processing block, we want to apply a 4 millimeter full width at half max Gaussian blur. You have other options here if you want them. You can blur in mask, which is often a nice choice. You can blur to a full width at half max, which is also often a nice choice, particularly if you have like data from multiple scanners. In that case, the amount of blur right out of the scanner, even if the the voxel grids are identical, the amount of blur right out of the scanner tends to be different. So blurring to a full width at half max is kind of a nice idea if you're acquiring data from multiple scanners. Mask EPI inat, yes. In the mask block by default, we compute a mask that seems to contain the brain in the EPI data. But that's often a little bigger than it ought to be. So if you want a tighter mask, particularly for multiple comparison correction, then you can add this option, and this option will intersect that default EPI mask with the skull stripped anatomical mask, and that will make the resulting EPI mask tighter. And then we have, now in the regress block, so we're on to the actual linear regression part, we give it our stimulus timing files. There's ev1viz.txt and ev2viz.odd.txt. Those are the stimulus onsets for the two runs and for the two conditions. And then we give corresponding labels for those files, so viz and odd are the labels that correspond to this the timing files. Regress basis is where we tell AFNI proc or 3D-deconvolve what basis function we want to use to model those events. So these are just onsets. But, so there's an event, the first visual event was at 60 seconds or 1 minute into the first run. How should 3D-deconvolve model that? Well, we want to use the BLOCK function, which is a specific wave shape, but we also want to tell it that the event lasts 20 seconds. So 3D-deconvolve will convolve this 15-second gamma variate basis function with a 20-second boxcar, and the result will be 20 plus 15 is 35 seconds. You'll get a 35-second response curve. And this one is just saying what height to make that response curve. If you allow me to go off on yet another tangent, if you wanted to see what that looks like, we'll see it soon enough, but I'll just mention this briefly. Timingtool.py, because this deals with stimulus timing, has a help underscore basis option. And if you run that, maybe pipe it through less or whatever, it babbles about the different basis functions. And for example, here's block D comma P. It tells you when the P cap ends. This is used to help compare these things. So you see a lot of basis functions in here. And at the bottom, it gives you an example of how you could run a 3D deconvolve command. Here we have, I'm saying there's a single event at time 0 in each one of these cases, and I want to model that event at time 0 with a GAM or a random wave function or a block function or SPMG3, and then I want to plot it, or plot it in a more complicated but prettier way so I know what's what. So you can look at the different curves. This doesn't apply to this example, but let me run this. So that was the 3D deconvolve command, and now I'll plot it. I'll just copy and paste this. And there are the curves from the bottom up. If I run this, put that in the background. Let's look at the last 20 lines so we can see the 3D deconvolve command. So now you see the 3D deconvolve command, and these are the basis functions. It goes actually from the bottom up. So here's a GAM, here's the wave curve, here's the block with a duration of 1 second. So you see that's pretty similar to GAM, but it's wider. And then SPMG3 is actually 3 curves, the canonical basis function, the temporal derivative, and the dispersion. But anyway, so that's an example of how you can just run a 3D deconvolve command with no data. You tell it the time grid, 200 time points at a TR of 0.1 second. And you can make an X matrix to just plot it and see what the single response curves look like, what the single basis functions look like. Anyway, so we use block 20, 1. We'll see what those look like too, but it's of course just a 20-second response curve. And then we want to censor places where it looks like the subject may have moved. So if motion, if time frame by frame motion seems to be too big, in this case if it is greater than or equal to 0.3 millimeters, 0.3, not 3 millimeters, but 0.3 approximate millimeters between 2 consecutive time points, we might censor those time points because if the subject moved, the data is not reliable. Also, we can censor outliers. We'll talk about what the outlier, how we evaluate outliers later, but that's just an additional censoring option that sometimes captures different motion than this one does. This one is based on the volume registration, but sometimes that doesn't capture all the motion. We want to regress out motion parameters per run. So we'll talk about the details of that later, but instead of 6 parameters across all 3 runs, we'll have 6 parameters per run, and so 18 regressors. Here's another one of those dash block underscore ops underscore something options. So here we're going to provide a bunch of options to pass directly to 3D deconvolve. So again, these are not AFNI proc options, these are 3D deconvolve options, and it's just for GLTs. Well, actually this one's to use 2 CPUs, but then we give it a couple GLTs, viz minus odd, and a label. So those will be passed directly to 3D deconvolve. I won't bother to go back to the proc script for that. Compute fits says that's a RAM saving device for 3D deconvolve. 3D deconvolve will fit the model to the data and then output the beta weights and output, in our case it will output the fit time series and the residual time series. But if you have the input and the fits and the residuals, that's a little redundant. So to save RAM, there's no point in having 3D deconvolve compute the fits because it knows the input and it knows the residuals. So in this case, we're saying don't bother computing the fits. We will compute it afterwards by just taking the input to the regression and subtracting the residuals. And that's again just to save RAM, because a lot of people are using laptops when they run these examples here. So sometimes that makes a difference. Here's another quality control measure. 3D Convolve or whatever, or RemelFit, well, 3D Convolve will generate the X matrix, and that has a bunch of ideal regressors for regressors of interest. Here we want to compute their sum, and this is just another quality control metric measure that I like to have when I look at other people's data to see if there's anything strange here, like if there's a gap in the timing, or if at some point the response functions seem to stack. It's just another way to look for peculiarities, or if the sum looks too much like a flat line. That might suggest being close to having a multicollinearity problem. We're going to estimate the blur in the EPI time series, that's the input to the regression, and the residuals output from the regression. So the residuals are where we usually care, but it's easy to compute them both just to see the numbers. We could run cluster simulation at the end of the regression. That's a correction for multiple comparisons at the single subject level. But the reason we're saying not to here is just to save time, which is probably less important now that we're just running through this with videos, but still maybe most users don't want to take the extra 10 or 12 minutes to run that on their laptop, so we'll just say no. Here we specify the form of the HTML review style. The default is basic, but when we have that other case where we've changed it to pythonic. And lastly, we tell 3D Convolve to not only generate the proc script, but to run it. So with that said, I think I'm just going to stop this video right here so I don't go too long, and then we'll fire off the analysis in the next one.